Four moons orbit Jupiter. They were born from the same disk of gas and dust at nearly the same time around the same planet. Three of them are alive. One is not. Callisto is almost the size of Mercury, stretching 4,821 kilometers across. Yet for more than 4.5 billion years, it has done almost nothing. Its surface is the most heavily cratered anywhere in the solar system. Every impact, every collision, every scar has remained almost exactly where it formed because nothing has ever erased them. Just next door, Io is erupting with hundreds of active volcanoes, launching sulfur hundreds of kilometers above its surface. Europa hides a global ocean beneath its fractured ice. Ganymede generates its own magnetic field, something no other moon has ever been confirmed to do. Callisto does none of it. It simply waits. Frozen, silent. Science describes it as undifferentiated, a remarkably simple word for an extraordinary idea. Deep inside, its rock and ice never fully separated into distinct layers. It never became the kind of organized world its siblings did. That was not an accident. Something happened at the very beginning of the solar system, or more precisely, something never happened. A difference measured not in millions of years, but in the earliest moments of Callisto's formation, when the laws of physics quietly sent four neighboring worlds down completely different paths. One became the most volcanic body in the solar system. One became one of the most promising places to search for life. One became the largest moon in the solar system, with a magnetic field unlike any other, and one became a frozen record of the day it was born. For decades, astronomers dismissed Callisto as Jupiter's dead moon, but that verdict has become increasingly difficult to defend because beneath a surface that appears unchanged for billions of years, scientists have found evidence suggesting there may be far more hiding inside than anyone once believed. Quick favor before we continue. If you find yourself coming back to videos like these, hit subscribe so you don't miss the next one. It makes a bigger difference than you might think. To understand why four sibling moons ended up living such radically different lives, we first need to go back to the day they were born. Long before spacecraft crossed the outer solar system, one winter night changed the way we understood the heavens. On the 7th of January, 1610, Galileo Galilei noticed four tiny points of light beside Jupiter. They shifted position from one evening to the next. Those lights were not distant stars at all. They were worlds in motion. He named them the Medicean stars. Today, we know them as Io, Europa, Ganymede, and Callisto, the four great Galilean moons. What makes their story remarkable is how similar it began. Each moon emerged from the same swirling disk of gas and dust that surrounded the young Jupiter after the giant planet formed. Planetary scientists call this structure a circumplanetary disk, meaning a ring of material circling a planet rather than a star. From that shared birthplace came four siblings with nearly the same age and many of the same ingredients. Yet time carried each one toward a remarkably different future. If we arrange them by distance from Jupiter, a pattern begins to appear. Closest is Io, orbiting at about 422,000 kilometers, which is about 262,000 miles. Beyond it comes Europa at roughly 671,000 kilometers, which is about 417,000 miles. Next is Ganymede at around 1,070,000 kilometers, that is nearly 665,000 miles. Farthest of all circles Callisto at approximately 1,883,000 kilometers, which is about 1,170,000 miles. That final step outward is enormous. Callisto travels almost twice as far from Jupiter as Ganymede. Distance becomes the thread that ties everything together. Around Jupiter, every additional stretch of space changes the strength of gravity, the amount of internal heating, and the long history written inside each moon. We will return to that relationship again and again because almost every mystery in this system grows from it. Geological activity simply means that a world's interior still produces enough heat to reshape its surface. That heat can feed volcanoes, crack icy crusts, lift mountains, or recycle ancient terrain into something new. When the interior cools too much, those engines fade. The landscape remains largely unchanged, preserving events that happened unimaginably long ago. But these moons did not begin with different recipes. They inherited comparable mixtures of rock and ice from the same nursery around the same giant planet. Their earliest circumstances were astonishingly alike, even before their paths slowly separated across billions of years. As we continue, keep that single principle close. Four siblings shared one birthplace, one parent, and one beginning. Yet only their distance from Jupiter steadily changed the balance of heat, motion, and transformation. Everything that followed grew from that simple arrangement, leaving each moon to tell a profoundly different version of the same ancient story. Across Callisto's ancient face lies a structure so immense that it reshapes your sense of planetary scale before you even understand what you are seeing. Its name is Valhalla. It is the largest multi ring impact basin known anywhere in the solar system, a mark left by a collision whose effects remain visible after billions of years. The bright central region stretches for about 600 kilometers, which is about 373 miles. From there, broad circular rings spread outward until the entire formation reaches nearly 3,800 kilometers, which is about 2,361 miles across. If that distance were laid across Earth, it would span roughly from London to Tehran, yet every curve belongs to a single impact. Planetary scientists estimate that the collision happened between 2 billion and 4 billion years ago. An object of extraordinary mass struck the icy crust at tremendous speed, releasing more energy in moments than human civilization has ever produced. The force briefly melted large portions of the frozen surface. Waves of pressure raced outward through the softened ground, much like ripples spreading across a pond after a stone falls into the water. Then the heat escaped into space. The surface hardened again. Every expanding wave became fixed in place, preserving a fleeting instant that would otherwise have vanished forever. Those broad rings are often mistaken for mountain chains. They are something far stranger. Each ring marks the frozen edge of a traveling ripple, captured as the landscape solidified before gravity and time could smooth it away. We are looking at motion that became permanent, but giant impacts leave more than visible scars. They also send immense seismic waves through an entire world. Seismic waves are vibrations that travel through the interior of a planet or moon after a violent event, carrying enormous amounts of energy. On Mercury, Earth's moon, and Mars, those waves eventually converge at the exact point opposite the impact. The focused energy breaks and uplifts the landscape there, producing rough, jumbled ground known as antipodal terrain, meaning terrain found at the opposite side of a globe. When the National Aeronautics and Space Administration spacecraft named Galileo flew past Callisto during May of 2001, its cameras examined the region directly opposite Valhalla. Scientists expected fractured hills and disrupted landforms. They found none. The terrain appeared remarkably ordinary, with no obvious signature of focused seismic destruction. That missing feature became one of the most intriguing observations ever made about Callisto. An absence can carry as much meaning as a discovery, especially when nature repeatedly follows the same pattern elsewhere. But before we weigh what that missing landscape might reveal, it helps to remain with the basin itself. Valhalla is older than the age of dinosaurs. It is older than complex multicellular animals. Its immense rings remain almost exactly where the impact left them, unchanged across spans of time that challenge imagination. How could a world this large lose every meaningful way of repairing the wounds carved into its surface? Some patterns in the universe are so precise that they resemble carefully arranged clockwork. Jupiter's three inner large moons follow one of those patterns every moment of every day, tracing a gravitational rhythm that has endured for billions of years. Yet as you watch that rhythm unfold, one moon never joins the sequence. Callisto circles nearby, forever outside the arrangement. Planetary scientists call this relationship the Laplace resonance, named after the French mathematician Pierre-Simon Laplace, who described its underlying mathematics during the 18th century. A resonance is a repeating gravitational pattern in which orbiting bodies continually influence one another, keeping their motions synchronized over immense spans of time. It sounds abstract. Its consequences are anything but. The timing is exact. Every time Ganymede completes one journey around Jupiter, Europa completes exactly two. During that same interval, Io completes exactly four. Their orbital periods remain linked like the gears inside an intricate mechanical clock, each revolution reinforcing the next through gravity alone. But this repeating pattern does far more than organize their motion. It constantly prevents their paths from becoming perfectly circular. Instead, each moon follows a slightly elongated orbit, called an elliptical orbit, meaning its distance from Jupiter changes during every circuit. At one point, the moon moves a little closer to the giant planet. Later, it drifts a little farther away. That continual change becomes the foundation of everything that follows. As the distance rises and falls, Jupiter's gravitational pull also changes. The moons are squeezed more strongly, then released slightly, then stretched again. Over countless orbits, this repeated flexing creates friction inside their interiors. Friction transforms motion into heat. Planetary scientists call this process tidal heating, meaning warmth generated by changing gravitational forces rather than by sunlight or radioactive decay. The amount of energy involved is astonishing. Io alone produces an estimated 100 trillion watts of heat through tidal friction. That is approximately twice the total heat escaping from Earth's interior, even though Io itself is slightly smaller than our own moon. Deep beneath its surface, gravity keeps working without pause. Callisto follows a very different path. Its orbit is almost perfectly circular, so its distance from Jupiter changes very little during each revolution. The giant planet pulls with nearly the same strength all the time. There is scarcely any repeated stretching. There is almost no internal friction. The great engine driving the neighboring moons never truly starts inside Callisto. That contrast is remarkably precise. From Callisto's surface, Jupiter still dominates the sky, and the neighboring moons continue their endless journeys nearby. Yet the gravitational partnership shaping Io, Europa, and Ganymede never includes the outer sibling. Callisto remains close enough to witness the consequences while missing the mechanism itself. We have now reached an important dividing line. Three moons entered a gravitational relationship that transformed their interiors across billions of years. One never did. If Callisto formed beside the others from the same material, why did that doorway remain closed to the largest moon after Ganymede? Imagine the young Jupiter surrounded by a broad disk of gas and dust that had not yet settled into its final shape. Nothing in that disk remained fixed for long. Every growing moon drifted through the material around it, pulled forward, slowed down, and nudged inward by countless small gravitational interactions. Their orbits evolved gradually, almost imperceptibly, over immense stretches of time. The remarkable orbital pattern we know today did not exist at the beginning. It emerged step by step as Io, Europa, and Ganymede migrated inward at slightly different speeds. Each moon eventually encountered a point where gravity could lock its motion to a neighbor. This process is called gravitational capture, meaning two orbiting bodies become linked in a repeating relationship that naturally maintains itself. First, one pair settled into a stable rhythm. Later, another pair joined. Over time, those individual links combined into the enduring pattern that now binds all three moons together. But Callisto traveled a different path from the very start. It formed farther from Jupiter, where material was spread more thinly, and it accumulated mass at a slower pace. Planetary scientists call this accretion, the gradual growth of a world as countless smaller pieces collide and merge into a larger body. Because that growth unfolded over a much longer interval, Callisto never migrated deeply enough into the disk to enter the region where gravitational capture could have taken place. The Great Resonance formed without its outer sibling. Recent studies published during the years 2025 and 2026 suggest another possibility as well. Within the circumplanetary disk itself, pressure may not have been distributed evenly. Researchers propose that a pressure bump, meaning a region where gas naturally piled up, could have acted like a barrier. Instead of allowing Callisto to continue drifting inward, that feature may have halted its migration entirely, leaving it stranded beyond the zone where the resonance developed. But distance alone was only part of the story. Timing mattered just as much. The newborn solar system contained a radioactive isotope called aluminum 26. An isotope is a version of an element whose atomic structure makes it unstable, causing it to release energy as it gradually changes into another element. Aluminum 26 carried an unusually brief half-life of only about 717,000 years. A half-life is the time required for half of a radioactive substance to decay, steadily reducing the heat it can provide. Io, Europa, and Ganymede formed early enough to trap meaningful amounts of that radioactive material inside their growing interiors. Its decay supplied an initial burst of warmth. While those moons were still assembling, Callisto grew more slowly. By the time much of its mass came together, most of the aluminum 26 had already disappeared. That early source of heat had largely faded away. So Callisto missed two crucial opportunities. It never joined the resonance, and it arrived too late to receive much of the earliest radioactive warming. Together, those circumstances kept its interior below a threshold crossed by nearly every other large world, preventing the transformation that would eventually reshape them from the inside out. There is a threshold that every large world hopes to cross during its earliest history. If enough heat builds inside, gravity begins rearranging the interior from the inside outward. Planetary scientists call this process differentiation. The word simply means that materials separate according to their density. Heavy substances such as iron and silicate rock sink toward the center, while lighter materials, including ice and water, gradually rise closer to the surface. Over time, a layered world emerges, with a core, a mantle, and a crust. Earth crossed that threshold. Mars crossed it. Our moon crossed it. Io, Europa, and Ganymede crossed it as well. Their interiors reorganized into distinct structures that continued shaping their futures long after their formation ended. But Callisto never fully made that transition. Instead, its interior appears to have remained a broad mixture of rock and ice, blended together rather than neatly sorted into separate layers. Researchers believe some limited separation may have occurred, yet nothing approaching the clear internal architecture found inside the neighboring moons. In many ways, Callisto still resembles an unfinished world, preserving an earlier stage that almost every other large planetary body eventually left behind. That makes it extraordinary. Among all the large objects in the solar system, Callisto stands as the largest known body that failed to complete differentiation. How can we know what lies so far beneath a surface we have never drilled? The answer comes from gravity. During repeated flybys, the Galileo spacecraft measured how Callisto's gravity tugged on the spacecraft as it passed overhead. Those tiny changes allowed scientists to calculate a property called the moment of inertia factor. This measurement describes how mass is distributed inside a rotating body. A perfectly uniform sphere has a value of zero point 0.4. Earth measures about 0.33 because its dense iron core concentrates mass near the center. Callisto measures approximately 0.3549. That value sits much closer to a uniform interior than to a strongly layered one, suggesting that a large metallic core never fully developed. But differentiation creates more than orderly layers. A metallic core can slowly circulate as heat escapes, producing electrical currents that generate a magnetic field. This circulation is called convection, meaning warmer material rises while cooler material sinks, creating continuous motion. Without a substantial metallic core, that process cannot operate in the same way. Callisto therefore lacks a global magnetic field generated from within its own interior. The consequences spread through the moon one after another. Without a strong internal magnetic field, energetic charged particles encounter less resistance. Without a well-organized mantle, internal heat cannot circulate efficiently. Without sustained internal warmth, volcanoes never awaken. Without volcanism, ancient terrain remains exposed instead of being buried beneath fresh material. Every impact stays where it landed. But that chain of events leaves behind something unexpectedly valuable. Across billions of years, Callisto's surface became a record instead of a canvas, preserving nearly every major collision since the early solar system. Its landscape did not erase history. It collected it. If you could drift above Callisto and trace your gaze across its landscape, you would eventually notice something unusual. The craters stop becoming individual landmarks. They blend into one another until the entire surface appears woven from overlapping circles, each preserving the memory of an ancient collision. Planetary scientists describe this condition with a specific term: saturated. In plain language, it means the surface has reached the greatest crater density it can sustain. Every new impact now tends to destroy or overlap an older crater, so the overall number no longer increases. That description carries remarkable implications. Saturation does not mean impacts have stopped. Quite the opposite. It means Callisto has continued collecting collisions since the earliest history of the solar system, while retaining almost every generation of damage along the way. Fresh craters arrive. Older ones are partly erased by those impacts alone, and the landscape remains permanently crowded. Compare that with Earth. Here, impact scars rarely survive for very long in geological terms. Flowing water cuts through them. Wind gradually softens their edges. Sediment buries them beneath newer layers. Plate tectonics slowly drags portions of the crust back into the planet's interior, while volcanic eruptions blanket older terrain beneath fresh rock. The Chicxulub impact crater, created about 66 million years ago by the collision linked to the extinction of the dinosaurs, has become difficult to recognize without careful geological investigation. But Callisto followed another path entirely. Craters formed more than 4 billion years ago still remain sharply outlined beside features perhaps only 400 million years old. Across that immense span, the landscape experienced almost no internal reshaping capable of wiping the record clean. One impact simply joined countless others already waiting across the surface. Current estimates place the age of much of Callisto's exterior at more than 4 billion years. In practical terms, you are looking at terrain dating back to the earliest chapters of solar system history. Few large worlds offer anything comparable. Most have rewritten their earliest landscapes many times over. Callisto largely kept its original pages intact. Each crater, therefore, becomes more than the mark of a collision. It preserves clues about the object that struck, including its approximate size, its incoming speed, and the angle at which it arrived. Studied together, millions of these scars create an extraordinary archive of bombardment stretching across nearly the entire lifetime of the solar system. Few records anywhere approach such continuity. But this remarkable preservation transformed Callisto into something unexpectedly valuable. Scientists use its cratered plains as a benchmark when comparing the ages of icy surfaces elsewhere because the record remains so complete. The moon became a reference point precisely through its refusal to change. Hidden within that vast archive lies another story as well. Among the countless impacts are unmistakable traces of a brief interval when collisions across the solar system surge dramatically beyond their usual pace. Callisto preserved that violent chapter with exceptional fidelity, keeping evidence of an era that altered nearly every major world orbiting the Sunday. There was a period when the solar system became far more dangerous than the orderly place we imagine today. Between roughly 4 billion, 100 million, and 3 billion, 800 million years ago, collisions increased across vast distances, striking worlds with extraordinary frequency. Planetary scientists call this interval the Late Heavy Bombardment, a name given to one of the most violent chapters in planetary history. Its traces remain scattered across the solar system. The ancient highlands of Earth's moon preserve countless craters from that era. Mercury bears enormous impact basins formed during the same interval. Mars still carries portions of the record despite later geological change. But among the largest worlds, few preserve the evidence as completely as Callisto, whose surface remained available to receive each new collision without rewriting what came before. The leading explanation reaches far beyond any single moon. Early in solar system history, Jupiter, Saturn, Uranus, and Neptune slowly shifted their orbital positions through countless gravitational interactions with one another and with surrounding debris. Those subtle migrations disturbed the asteroid belt and other reservoirs of rocky material. Vast numbers of objects were thrown onto new paths, many crossing the orbits of planets and moons that had previously escaped such relentless bombardment. For a comparatively brief span of cosmic time, impacts arrived at a rate unlike anything seen since. Young planetary surfaces that had only recently formed were struck repeatedly before they had any opportunity to settle. Some collisions excavated enormous basins. Others shattered older craters, creating layers of overlapping destruction that remain visible billions of years later. But each world responded according to its own internal nature, Callisto received impact after impact and retained them. Io, driven by relentless volcanic activity, continually buried comparable evidence beneath fresh lava. Europa renewed its icy shell over millions of years, gradually removing much of the ancient record. The same barrage reached neighboring moons, yet only one preserved it with remarkable completeness. This interval carries another significance for us. Many researchers believe the late heavy bombardment overlapped with the earliest stages during which life may have emerged on Earth. Some impactors delivered complex organic molecules, meaning carbon-based compounds capable of participating in the chemistry associated with living systems. Earth already possessed liquid water and active geological energy, allowing those ingredients to interact within an evolving environment. Callisto encountered many of the same incoming objects. Organic, rich material almost certainly arrived there as well, but the conditions awaiting those compounds differed profoundly. There was no broad reservoir of liquid water near the surface, no sustained internal heat capable of driving extensive chemical reactions, and no active geology to recycle materials into new environments. The same cosmic storm reached both worlds, their futures separated immediately afterward. For Earth, those impacts may have contributed to one of the greatest transformations in natural history. For Callisto, they simply expanded an already growing archive written across ice and rock. But if you want to understand what sustained internal heating can truly accomplish, we need only turn our attention inward toward Jupiter's nearest large moon, where gravity never stopped, reshaping the world beneath its surface. To see what the missing resonance truly cost Callisto, we have to shift our attention inward toward Jupiter's closest large moon. Io occupies the deepest part of that gravitational relationship, where the repeated pull of Jupiter and its neighboring moons reaches its greatest intensity. Everything about Io reveals what sustained tidal heating can accomplish when it never has a chance to fade. Among all known worlds in the solar system, none surpasses Io in volcanic activity. Even Earth, with its mountain ranges, ocean ridges, and thousands of volcanoes, cannot match the relentless pace of change unfolding there. The landscape is in constant transformation, driven from below by extraordinary amounts of internal energy. The source is the same tidal heating we explored earlier, now operating at its most powerful. As Io follows its slightly stretched orbit, Jupiter's gravity continually squeezes and relaxes the moon. That endless flexing generates friction throughout the interior, keeping large regions close to the melting point. Scientists estimate that this process releases roughly 100 trillion watts of heat, an astonishing amount for a world slightly smaller than Earth's moon. The consequences reach the surface everywhere we look. Hundreds of volcanic centers remain active across Io, each connected to reservoirs of molten rock beneath the crust. Some eruptions throw sulfur and sulfur dioxide high above the landscape in immense umbrella-shaped plumes. The tallest rise nearly 300 kilometers, which is about 186 miles, above the surface before the material slowly falls back, spreading fresh deposits across vast regions. Those deposits give Io an appearance unlike any other moon. Sulfur exists there in several different forms, each reflecting light differently, depending on its temperature and chemical state. Brilliant yellow plains merge into orange fields. Deep reds border darker volcanic regions. White frost appears beside black lava flows. The colors shift over time as new eruptions continually repaint the surface. But perhaps the most remarkable feature is something you will struggle to find at all. Impact craters are almost entirely absent. Asteroids and comets certainly strike Io, just as they strike every other moon in the solar system, their scars simply do not survive for long. Fresh lava spreads across older terrain, burying each crater beneath new volcanic layers before another generation can accumulate. Geological activity renews the landscape so rapidly that the average surface age is estimated to be only a few million years. Now place that beside Callisto. One world preserves terrain more than 4 billion years old. The other continually replaces terrain that is only a few million years old. They formed around the same giant planet from closely related material during the same early chapter of solar system history. Yet a difference measured in orbital distance changed everything, allowing one moon to become an ever-changing volcanic world while the other remained an enduring archive. But Io represents only one possible outcome. The same gravitational engine that powers endless volcanism, there also created conditions on another neighboring moon that may be even more significant when we begin asking where life could exist beyond Earth. Size alone does not decide a world's destiny. Europa proves that almost immediately. Although it measures only about 3,121 kilometers across, which is about 1,940 miles, compared with Callisto's 4,821 kilometers, which is about 2,996 miles. This smaller moon holds an astonishing secret beneath its frozen exterior. Current evidence indicates that Europa contains more liquid water than all of Earth's oceans combined. Its location would seem to make that impossible. Europa circles the Sun at roughly 628 million kilometers, which is about 390 million miles, where sunlight alone cannot keep vast quantities of water from freezing solid. But the heat sustaining that hidden ocean does not come from the sunday, it comes from within. The same gravitational resonance that continually reshapes Europa's orbit also generates enough tidal heating to maintain an immense global ocean beneath the ice. Scientists estimate that this buried ocean extends somewhere between 60 kilometers, which is about 37 miles, and 150 kilometers, which is about 93 miles, in depth. Above it rests an icy shell estimated to be between 10 kilometers, which is about 6.2 miles, and 30 kilometers, that is nearly 19 miles, thick. That shell never remains completely unchanged. Repeated tidal flexing fractures the ice, opens long cracks, and allows portions of the surface to freeze again in new patterns. The result is a world covered by sweeping ridges and intersecting bands rather than dense fields of ancient craters. Its youth becomes unmistakable. Estimates place the average age of Europa's visible surface between roughly 20 million and 180 million years. Compared with the immense antiquity preserved by Callisto, Europa appears almost newly formed. The difference is measured not only in years, but in the constant renewal taking place beneath your imagined footsteps. But perhaps the most intriguing feature lies below the ocean itself. Europa's liquid water appears to rest directly upon a rocky seafloor. That contact allows tidal energy to drive chemical reactions between water and rock, creating hydrothermal environments similar to those found around deep-sea vents on Earth. Entire ecosystems flourish around such vents in our own oceans without depending on sunlight, drawing energy instead from chemical processes rising through the crust. For that reason, Europa has become one of the leading places in the solar system where scientists search for conditions favorable to life. The interest does not arise from its distance from the sun or from chance. It grows directly from the persistent energy supplied by gravitational interactions that never cease. But the comparison with Callisto becomes even more surprising. Callisto is larger. It formed from the same circumplanetary disk. It also contains an enormous amount of water ice, roughly half its total mass. Some evidence even hints that liquid water may exist beneath its surface as well. The crucial difference is energy. Europa receives a continual supply. Callisto receives only a small fraction of that warmth. Whether a hidden ocean can survive under those conditions remained uncertain until one spacecraft, carrying remarkably sensitive instruments, began passing repeatedly through the Jupiter system. For centuries, Callisto seemed content to reveal almost nothing. Planetary scientists often described it as the least interesting of the large worlds orbiting Jupiter, an object valued mainly because its ancient surface preserved an exceptional crater record. Some researchers even referred to it as an ugly duckling, little more than a hunk of rock and ice that served as a convenient benchmark for comparing more dynamic worlds. But that perception began to change with a mission launched by the National Aeronautics and Space Administration in October of 1989. After a long journey across the solar system, the Galileo spacecraft entered orbit around Jupiter in December of 1995. During the years that followed, it completed 12 close flybys of Callisto, gradually replacing assumption with direct measurement. One instrument proved especially important. Galileo carried a magnetometer, a device designed to measure the strength and direction of magnetic fields surrounding planets and moons. As the spacecraft repeatedly passed Callisto, the readings revealed something that refused to fit the old picture. The magnetic signal changed in a regular pattern, matching Callisto's position as it traveled through Jupiter's enormous rotating magnetic field. That repeating behavior pointed toward a process known as electromagnetic induction, the generation of electrical currents inside a material when an external magnetic field changes around it. Jupiter's magnetic field swept across Callisto during every orbit. If the moon contained a layer capable of carrying electricity, those changing conditions would produce electrical currents. Those currents would then create a secondary magnetic field, exactly the kind Galileo detected. The explanation narrowed quickly. Dry rock conducts electricity very poorly. Pure water ice also resists the flow of electrical current. But salty liquid water behaves very differently. Dissolved salts separate into electrically charged particles that move freely through the liquid, allowing electrical currents to pass with remarkable efficiency. Among the known materials expected inside Callisto, a salty ocean offered the strongest match to the observations. Suddenly, the supposedly lifeless moon appeared far more intriguing than anyone had imagined. Beneath a battered landscape that seemed frozen since the earliest chapters of solar system history, there was now compelling evidence that a hidden, conductive layer still existed. The simplest interpretation placed that layer deep below the crust as a global ocean enriched with dissolved salts. But liquid water alone does not answer the question that naturally follows. Water can exist under very different conditions, and those conditions shape everything that happens within it. The hidden ocean inferred inside Callisto would occupy an environment profoundly different from the one thought to exist inside Europa, despite the shared ancestry of these neighboring moons. To understand what that difference truly means, we need to leave the surface behind and descend through the layers, separating ancient ice from the buried sea that may still endure far below it. Imagine descending beneath Callisto's battered surface instead of crossing it. The deeper we travel, the stranger its interior becomes, because almost every expectation formed from Earth, the Moon, or even Europa, begins to lose its shape. Callisto never completed the internal transformation that organized its neighboring worlds. The best models available today describe an enormous outer region made from a mixed blend of ice and rock rather than neatly separated layers. Instead of a sharp boundary dividing one material from another, the composition changes gradually with depth. Ice becomes a little less abundant. Rock becomes a little more common. Gravity begins to favor denser material, yet the process never reaches the orderly arrangement seen elsewhere. But the picture grows even more intriguing farther down. At a depth estimated between 100 kilometers, which is about 62 miles, and 250 kilometers, that is nearly 155 miles, researchers believe a liquid layer may exist. This hidden ocean, inferred from the magnetic measurements collected by the Galileo spacecraft, would rest beneath the mixed outer shell while remaining enclosed by frozen material above and a progressively rockier interior below. Keeping water liquid so far from the sun demands an explanation. Scientists think dissolved salts provide part of the answer. Another possibility is ammonia mixed into the water. Ammonia lowers the freezing point, meaning liquid can persist under colder conditions than pure water alone would allow. Combined with immense pressure deep inside the moon, that chemistry could preserve a buried sea across extraordinary spans of time. Yet this ocean, if present, differs profoundly from the one beneath Europa. Europa appears to place liquid water directly against a rocky seafloor, allowing minerals, heat, and chemical reactions to circulate into the ocean. Those interactions are considered especially important because they provide energy and ingredients capable of sustaining complex chemistry. Callisto seems to interrupt that connection. A broad region of partially separated ice and rock lies beneath the suspected ocean, reducing direct contact between liquid water and the deeper rocky material. Below that hidden layer, the interior continues as an uneven mixture of ice, rock, and metallic material extending toward the center. There is no clearly defined metallic core. There is no distinct rocky mantle. The internal architecture remains incomplete, preserving the signature of a world that never fully reorganized after its birth. But some warmth still survives. The remaining source comes from the gradual radioactive decay of naturally occurring elements, including uranium, thorium, and potassium 40, trapped within the rocky portions of the moon. Their energy is released exceedingly slowly across billions of years, producing only a faint supply of heat. It is scarcely enough, yet it may be sufficient to prevent every part of the hidden ocean from freezing solid. Now, the mystery of Valhalla begins to resolve itself. A giant impact sent tremendous seismic energy racing through Callisto long ago, yet the opposite side of the moon never developed the disrupted landscape seen on other worlds. The explanation lies inside. That ancient shock passed through an interior lacking the rigid, fully differentiated structure needed to focus those waves into a single scar, leaving only the original wound to endure across deep time. Stand for a moment at the point exactly opposite Valhalla, on the far side of Callisto. You would never guess that an impact of unimaginable violence once shook the entire moon. The landscape appears familiar, covered with ancient craters and weathered ice, offering no obvious sign that tremendous energy should have converged there long ago. When a massive object collides with a planetary body, the force of that impact does not remain confined to the crater itself. Powerful seismic waves spread outward in every direction, passing through the interior before converging at the antipode, the point directly opposite the impact. If enough energy survives the journey, the returning waves can fracture the crust, lift hills, carve grooves, and leave behind terrain unlike anything surrounding it. We have seen this pattern before. Mercury preserves a striking example opposite the immense Calorus Basin, where the focused energy produced rugged, chaotic landscapes unlike the plains nearby. Comparable signatures also appear opposite the Moon's Imbrium Basin and at several other giant impact structures scattered across the solar system. Across very different worlds, the same physical process leaves a recognizable fingerprint. But when the Galileo spacecraft photographed the region opposite Valhalla during its flyby in May of 2001, that expected fingerprint was missing. Scientists searched for broken terrain, unusual ridges, or disrupted patterns that would betray the arrival of focused seismic waves. Instead, they found an ordinary stretch of ancient cratered ground. Nothing suggested that one of the largest impact basins in the solar system lay on the opposite side of the globe. That absence demanded an explanation. Seismic energy does not simply disappear without reason. If the waves failed to reshape the antipode, something inside Callisto must have weakened them before they completed their journey through the moon. A buried liquid layer provides exactly that kind of mechanism. Water absorbs and scatters seismic energy far more effectively than solid rock or solid ice. As the waves traveled through the rigid outer shell, they would eventually encounter a deep ocean if one existed. Entering that liquid region, much of their energy would disperse instead of remaining tightly focused. By the time the weakened waves reached the antipode, they would no longer possess the strength required to fracture the surface or create chaotic terrain. But this observation becomes even more compelling when viewed beside the magnetic measurements gathered by Galileo. Those magnetic data pointed toward an electrically conductive liquid hidden beneath the surface. The missing antipodal disruption points toward a layer capable of absorbing seismic energy. Two completely different investigations, relying on different physical principles, converge on the same remarkable possibility. We are left with a moon that outwardly resembles a frozen relic from the dawn of the solar system, yet repeatedly hints at something concealed beneath its ancient shell. The greatest surprise is no longer that scientists expected Callisto to be geologically lifeless. It is that every careful measurement has begun to reveal a more complicated world, forcing us to reconsider what a seemingly dormant moon may still be hiding, and how that changes everything we thought we understood about it. Instead of gleaming like a polished sphere of ice, Callisto appears subdued against the darkness surrounding Jupiter. Its surface reflects only about 20% of the sunlight that reaches it, giving the moon what planetary scientists describe as a low albedo, a measure of how much incoming light a surface reflects. Europa, by comparison, returns roughly 60 to 70% of that light, making the difference immediately apparent even from a distance. As we look more closely, that darkness proves uneven. Bright patches emerge from crater floors, central peaks, and freshly fractured terrain where powerful impacts have excavated cleaner water ice from below. Across much of the remaining landscape, however, a darker coating blankets the surface. It has endured for immense spans of time, yet its exact origin remains one of Callisto's unresolved mysteries. But researchers have assembled a compelling explanation. Far beyond Callisto orbit numerous small irregular moons captured by Jupiter long after the giant planet formed. These distant objects are dark, ancient bodies that gradually shed tiny grains of dust through countless collisions and continual impacts from smaller debris. Over millions of years, that material slowly spirals inward, spreading across the Jovian system until some of it settles onto Callisto. The pattern left behind matches what scientists expected. The hemisphere facing forward as Callisto travels around Jupiter accumulates more of this drifting material because it continually encounters the incoming dust first, Much like the front windshield of a moving vehicle gathers more insects than the rear window. This uneven darkening strongly supports the dust infall model and resembles the same process believed to have produced the striking contrast across Saturn's moon Iapetus. Another process gradually deepens the effect. Even at Jupiter's immense distance from the Sun, sunlight slowly removes surface ice through sublimation, the direct transformation of solid ice into vapor without becoming liquid first. As the brighter ice disappears, molecule by molecule, darker rocky particles and complex carbon rich material remain behind. Over time, this residue forms an increasingly concentrated blanket across exposed regions, making the surface progressively less reflective. But Callisto continues to reveal subtle activity. Carbon dioxide has been detected across portions of the surface, escaping gradually from icy material and contributing to an exceedingly thin atmosphere surrounding the moon. That atmosphere is extraordinarily sparse, containing far fewer particles than even the best laboratory vacuum produced on Earth. Yet it demonstrates that Callisto is still exchanging material with space in remarkably slow ways. Scientists have also identified organic compounds scattered across the surface. These are carbon bearing molecules commonly found within asteroids, comets, and many outer solar system bodies. They should never be mistaken for evidence of living organisms. Instead, they represent one ingredient considered important for biology. Callisto appears to possess organic chemistry. It may also conceal liquid water beneath its crust, but the remaining ingredient, a dependable source of energy capable of sustaining long-term chemical activity, is almost entirely absent. That missing ingredient shapes everything that follows, beginning with the delicate atmosphere that still clings to this ancient world and the faint clues it offers about processes continuing today. From a great distance, you might assume Callisto has no atmosphere at all. That impression is understandable, yet the moon does possess one, although the word itself needs careful qualification. What surrounds Callisto is so extraordinarily sparse that it challenges our everyday idea of what an atmosphere should be. Its exosphere, a region where particles are so widely separated that they rarely encounter one another, consists primarily of carbon dioxide with probable traces of molecular oxygen. The pressure at the surface is estimated to be roughly 10 billion times lower than the pressure at Earth's sea level. Even the finest laboratory vacuum chambers, created by humans, contain matter more densely packed than the gas surrounding this distant moon. That difference changes everything. Individual molecules released from the surface are far more likely to drift into space than to collide with neighboring particles. Instead of behaving like the thick envelopes surrounding Earth or even Mars, Callisto's exosphere resembles a fleeting collection of wandering molecules, sharing the same destination for only a brief time. They occupy the same region, yet scarcely interact before gravity loosens its hold. But another discovery complicated that simple picture. During its repeated encounters with Callisto, the Galileo spacecraft identified an ionosphere, a layer of electrically charged particles suspended above the moon. Such layers are usually associated with more substantial atmospheres, making its presence unexpectedly strong compared with the fragile exosphere below. The explanation reaches outward toward Jupiter itself. Although the giant planet's radiation environment is approximately 300 times weaker at Callisto than it is around Europa, energetic particles still stream across the moon. Those particles strike escaping carbon dioxide and other gases, removing electrons and creating electrically charged atoms and molecules. In this way, the ionosphere is continually renewed even while the underlying atmosphere remains exceedingly thin. The source of that carbon dioxide appears to be the surface itself. Frozen material mixed within Callisto's crust slowly undergoes sublimation, a process in which solid material transforms directly into gas without first becoming liquid. As molecules escape upward, others gradually emerge from below, producing a delicate balance between loss and replenishment. That equilibrium may have endured across billions of years, with almost imperceptible change. But Callisto is changing nonetheless. Tiny impact craters soften over immense spans as loose material creeps downhill beneath the moon's modest gravity. Only about 1/8 of the gravitational pull experienced on Earth. Frost migrates between slopes illuminated by the sun and those remaining in darkness during each rotation, lasting about 16.7 Earth days. These transformations unfold at a pace that challenges ordinary human imagination. Nothing here is truly motionless. Everything simply unfolds with extraordinary patience. We have now encountered organic compounds and persuasive evidence for buried liquid water, two ingredients widely considered important for biology. Yet one requirement remains elusive: sustained energy, capable of driving long-lasting chemical reactions, appears to be present only in the faintest measure. That missing ingredient becomes the defining reason Callisto stands apart from more promising ocean worlds, even while concealing remarkable secrets beneath its ancient crust. Some discoveries become more intriguing the longer we examine them. Callisto belongs to that rare group. Once the possibility of a buried ocean entered the scientific picture, this ancient moon joined a remarkably short list of places in our solar system where life could, at least in theory, exist. Its companions on that list include Europa, Enceladus, Titan, and Ganymede, each offering a different combination of conditions that invite careful investigation. As we continue our journey, you can reduce the question to three essential ingredients. Scientists generally agree that life as we know it requires liquid water, organic molecules, and a dependable source of chemical energy capable of driving reactions over immense spans of time. Remove any one of those pieces, and the pathway toward biology becomes far more uncertain. Callisto appears to satisfy two of those requirements. Evidence gathered across previous observations suggests a buried liquid ocean may rest beneath its outer layers, although its exact extent remains under investigation. Organic compounds have also been identified across the surface, and researchers expect similar carbon-bearing material to exist throughout the mixed interior of ice and rock. These ingredients are significant, yet they do not complete the picture. But the third requirement changes everything. Energy does far more than warm an environment. It keeps chemical reactions active, circulates nutrients, reshapes minerals, and creates fresh opportunities for increasingly complex molecules to form. Without a continuing supply of energy, chemistry gradually slows until it approaches a state of equilibrium where very little changes over time. Europa offers a striking comparison. There, tidal forces generated by orbital resonance continually flex the moon, heating its interior and sustaining circulation within its global ocean. The same energy is thought to power hydrothermal activity, where liquid water meets the rocky seafloor, producing environments comparable to deep ocean systems on Earth that support thriving ecosystems without any dependence on sunlight. Enceladus presents another example, releasing warm plumes rich in water and dissolved materials from fractures that connect directly to its hidden ocean. Callisto follows a different path. If its ocean exists, the principal heat source is believed to be the gradual radioactive decay of elements such as uranium, thorium, and potassium-40 contained within its rocky material. That process releases only a modest amount of energy across billions of years. The ocean is therefore expected to remain comparatively cold, chemically sluggish, and only weakly connected to deeper rock where fresh reactions could occur. But this distinction carries enormous weight. The National Aeronautics and Space Administration considers Callisto the least favorable among the known ocean moon candidates for supporting life, not because liquid water appears absent, nor because organic chemistry seems missing, but because the available energy budget is dramatically smaller than that of its more active neighbors. There is a certain precision to Callisto's story. Across more than 4 billion years, it may have preserved water and organic material while missing the final ingredient through nothing more than its place in the Jovian system. As we continue, another nearby moon reveals how a slightly different orbit transformed almost the same starting materials into a profoundly different world. Imagine placing two worlds side by side at the beginning of the solar system, giving each nearly the same ingredients, nearly the same birthplace, and nearly the same amount of time. You would expect their histories to unfold together. Yet, Callisto and Ganymede demonstrate how a remarkably small difference can reshape an entire planetary future. Ganymede is the largest moon in the solar system, measuring 5,268 kilometers across, that is nearly 3,273 miles. It is even larger than the planet Mercury, although Mercury contains considerably more mass because its rocky interior is much denser. Ganymede and Callisto formed within the same disk of gas, dust, rock, and ice surrounding the young Jupiter. Their overall compositions are strikingly similar, with each containing roughly equal proportions of rock and water ice by mass. But their interiors tell completely different stories. Ganymede experienced full differentiation, the process in which heat allows dense materials to sink toward the center while lighter materials rise above them. Over time, this sorting created a distinct iron core, a rocky mantle, and an extensive outer shell dominated by ice. Callisto, as we have seen, never completed that transformation. Its interior remains a broad mixture rather than a neatly organized structure. That difference extends far beyond internal appearance. Ganymede possesses its own magnetic field, making it the only moon in the solar system known to generate one through internal processes. Scientists attribute that field to motions within its molten metallic core, where circulating electrically conductive material creates magnetism through continuous movement. Around that organized interior, evidence also points toward multiple layers of ice enclosing a deep subsurface ocean. Callisto followed another path. Without enough internal heat to separate its materials, no comparable metallic core developed. Without such a core, no internally generated magnetic field emerged. The contrast reaches back to orbital history rather than composition alone. Ganymede spent its existence within the gravitational rhythm known as the Laplace resonance, receiving repeated tidal flexing that supplied heat over immense spans of time. Callisto remained outside that arrangement and escaped most of those warming effects. The Galileo spacecraft revealed this divergence with remarkable precision through measurements of gravity. Those observations produced a quantity called the moment of inertia factor, a value describing how mass is distributed inside a rotating body. Lower values indicate that more mass has gathered toward the center. Ganymede measures approximately 0.31, consistent with a dense central core. Callisto measures approximately 0.3549, indicating that much of its mass remains spread more evenly throughout its interior. But perhaps the greatest surprise is how little separated them. Two neighboring moons, formed from nearly identical materials within the same planetary system. One evolved into a layered world with its own magnetic field and a complex hidden interior. The other became a vast frozen archive, preserving conditions from the dawn of the solar system. Between those outcomes lies less than 1 million kilometers, that is nearly 621,000 miles, of orbital distance, a surprisingly modest separation that determined how much heat each world received across billions of years. If we were able to reduce Callisto's entire history to a single calculation, it would resemble a planetary balance sheet. Every source of heat added to one side. Every pathway for cooling appeared on the other. Across billions of years, that balance determined whether this moon would awaken internally or remain largely unchanged beneath its frozen exterior. When Callisto formed, three principal heat sources were available. The first came from accretional heating, the warming produced as countless pieces of rock and ice collided and released their kinetic energy. The second came from radiogenic heating, generated through the natural decay of radioactive elements embedded within rocky material. The third arose from tidal heating, created when Jupiter's gravity repeatedly flexed a moon's interior, converting mechanical stress into heat. But Callisto received only modest contributions from each of these sources. Models of its formation suggest that the moon accumulated slowly, perhaps over a period ranging from 100,000 years to as much as 10 million years. That leisurely growth proved decisive. Heat generated by incoming impacts escaped into space almost as rapidly as it formed because the surface had ample time to cool between successive stages of assembly. Another opportunity slipped away at nearly the same moment. Aluminum 26, a radioactive isotope that released tremendous quantities of heat early in solar system history, decays rapidly on geological timescales. Worlds that assembled quickly trapped much of that energy within their interiors. Callisto formed too gradually. By the time large portions of the moon had accumulated, much of the available aluminum 26 had already disappeared through radioactive decay, leaving far less heat to warm the growing interior. The final difference proved even more consequential. Unlike Io, Europa, and Ganymede, Callisto never became part of the orbital resonance that continually flexed neighboring moons. Io alone receives approximately 100 trillion watts of tidal heating today. For Callisto, that contribution was essentially absent. The most powerful long-term heat source available to the other Galilean moons simply never arrived. Scientists estimate that differentiation required the interior to remain near the melting point of its ice, roughly 270 Kelvin, long enough for dense materials to separate from lighter ones under pressure. According to current formation models, Callisto approached that threshold. It simply failed to remain above it for sufficient time. The difference was surprisingly narrow, a thermal near miss measured in accumulated energy rather than dramatic circumstance. But the consequences unfolded across every level of the moon's evolution. Without sustained melting, no complete internal layering developed. Without a metallic core, no internally generated magnetic field emerged. Without continuing tidal heat, geological activity gradually faded until only the faint warmth from uranium, thorium, and potassium 40 remained. That lingering radioactive decay may still produce roughly 10 to 20 trillion watts spread throughout a body measuring 4,821 kilometers across, which is about 2,996 miles. It appears sufficient to preserve a possible buried ocean, yet far too little to transform the surface above. From that single deficit, an entire chain of consequences continued outward, eventually shaping the radiation environment that surrounds Callisto today. There is one absence inside Callisto that shapes everything above it. You cannot see it from orbit, and no crater reveals it directly. Yet its consequences extend from the deepest interior to the highest edge of the moon's fragile exosphere. Callisto never developed its own global magnetic field. A planetary magnetic field forms when electrically conductive liquid circulates deep inside a world. That moving fluid acts as a natural generator, converting internal motion into magnetism. Earth accomplishes this through convection within its molten iron core. Ganymede does as well, making it the only moon in the solar system known to generate its own magnetic field. But Callisto never formed the distinct metallic core required for that process, so no protective magnetic shield surrounds the moon. Jupiter presents the opposite extreme. Its magnetic field is the largest created by any planet in the solar system, stretching millions of kilometers into surrounding space, which is about hundreds of thousands of miles beyond the orbits of its major moons. That immense magnetic environment traps vast numbers of energetic charged particles, creating radiation belts that dominate much of the Jovian system. Fortunately for Callisto, distance changes everything. Orbiting well beyond Jupiter's most intense radiation belts, the Moon experiences surface radiation levels approximately 300 times lower than those measured on Europa. That difference carries enormous practical consequences. Europa receives such relentless bombardment from high energy particles that an unprotected human standing on its surface would receive a fatal radiation dose in less than a single day. Callisto offers a far less hostile environment, but the moon is hardly untouched. Without an internal magnetic shield, its surface remains directly exposed to the solar wind, the continuous stream of charged particles flowing outward from the sun, along with energetic cosmic rays arriving from far beyond our solar system. Those particles steadily modify surface minerals through radiation-driven chemistry, gradually altering the composition of exposed ice and rocky material over immense spans of time. The same energetic impacts also knock atoms and molecules from the surface itself, a process known as sputtering, meaning energetic particles physically eject material into space. Some of that liberated material contributes to Callisto's exceedingly thin exosphere, while other particles escape Jupiter's domain entirely. Nothing happens quickly, yet the process never truly stops. These conditions gradually darken portions of the surface, especially across the leading hemisphere that encounters incoming dust and radiation first during its orbit. The changes accumulate grain by grain, molecule by molecule, preserving the slow rhythm that has characterized Callisto throughout nearly all of its existence. But this unusually moderate radiation environment has inspired practical thinking as well as scientific curiosity. During the 1990s, studies supported by the National Aeronautics and Space Administration identified Callisto as the most realistic staging location for future human exploration of the Jovian system. Its comparatively manageable radiation, remarkable geological stability, and solid icy surface combined into a rare advantage among Jupiter's moons. If people someday establish a lasting foothold around Jupiter, the first enduring outpost may rise upon the ancient landscape of the moon that seemed least remarkable for so very long. Imagine choosing a place to build humanity's first permanent foothold around Jupiter. The decision would seem obvious at first. We might expect the most active or scientifically dramatic moon to win. But decades of mission planning gradually pointed toward a different destination, one defined by restraint rather than spectacle. During the early years of the 21st century, Studies prepared for the National Aeronautics and Space Administration identified Callisto as the preferred staging post for future human operations throughout the Jovian system. The reasoning was remarkably practical. Every nearby alternative carried hazards that greatly complicated long term occupation. Europa promised extraordinary science, yet its surface receives radiation intense enough to become fatal for an unprotected human within less than a day. Io offered another challenge altogether. Constant volcanic activity reshapes its landscape so frequently that landing sites could change between visits. Ganymede possesses many advantages of its own, yet it still spends much of its orbit deeper within Jupiter's powerful radiation environment than Callisto does. But Callisto lies beyond the main radiation belts, where exposure falls into levels that properly shielded spacecraft and habitats can realistically tolerate over extended missions. Equally important, its surface has remained geologically stable for more than 4 billion years. Landing zones do not disappear beneath lava. Ground conditions change at an almost imperceptible pace. Engineers value predictability, and Callisto provides it in abundance. Its surface gravity reaches only about 0.126 times that of Earth, slightly lower than the Moon's approximately 0.166 times Earth gravity. Every structure, rover, and storage facility could therefore be assembled with far less supporting material than similar construction would require on our own planet. Heavy equipment becomes easier to transport. Large habitats become easier to expand. Resources strengthen the case further. Water ice exists across much of the surface and likely continues throughout the shallow subsurface. That frozen reserve could supply drinking water, oxygen through electrolysis, which is the separation of water into oxygen and hydrogen using electricity, and hydrogen suitable for future rocket fuel. A settlement would not need to import every essential resource across the immense gulf between Earth and Jupiter. But Callisto would probably never become the primary scientific destination itself. Instead, it could function as the logistical heart of an entire exploration network. Human crews might remain within comparatively safer conditions, while robotic spacecraft, autonomous landers, and remotely operated vehicles traveled onward toward Europa, Ganymede, and even Io, returning data without exposing astronauts to the harshest environments. Life there would demand careful planning. One complete rotation lasts about 16.7 Earth days, creating extraordinarily long periods of daylight, followed by equally prolonged darkness. Power generation, temperature control, and daily routines would all reflect that unusual rhythm. Above every habitat, one sight would never fade. Jupiter would span about 1.7 degrees across the sky, roughly 3.5 times wider than the full moon appears from Earth. Its cloud bands, changing storms, and immense presence would dominate every horizon. In the end, Callisto's value comes from the very quality that once made it seem forgettable. Its enduring stability preserves both the past of the Jovian system and perhaps the future of our exploration within it. Some worlds become valuable because they change, others become valuable because they refuse to. That realization transformed the way planetary scientists came to see Callisto, whose apparent lack of activity eventually became one of its greatest scientific strengths. Across most large planets and moons, ancient impact scars are erased by volcanism, tectonic forces, flowing ice, erosion, or buried beneath newer terrain. Each episode removes another chapter from the geological record. Callisto followed a different path. Its surface has accumulated impact craters almost continuously since the earliest stages of the solar system, preserving a history that very few large worlds still possess. Because of that remarkable continuity, researchers use Callisto as a reference point for crater size frequency distribution, meaning the number of craters of different sizes found across a given area of terrain. That distribution provides a benchmark for estimating the ages of distant icy landscapes whose histories cannot be measured directly. When scientists examine portions of Ganymede, Titan, objects within the Kuiper Belt, or other frozen worlds beyond the asteroid belt, they compare crater densities with the well-preserved record found on Callisto. Working backward through models of the changing impact rate over billions of years, they can estimate when those distant surfaces last experienced significant geological renewal. Callisto supplies the baseline from which those calculations begin, but its importance reaches even deeper into planetary history. The Moon still preserves abundant evidence from the late heavy bombardment, the era during which the young solar system endured an extraordinary barrage of collisions. The sizes, shapes, and abundance of those ancient craters preserve clues about the population of impacting bodies that once swept through the outer planets. Every surviving basin contributes another piece to that long, vanished environment. You could think of Callisto as the ruler placed beside every other icy moon. Its own landscape has become the standard against which geological clocks are compared. Rather than obscuring the past, its remarkable stability allows the past to remain visible. Few worlds can offer such consistency across more than 4 billion years. This is an unusual kind of scientific importance. Callisto rarely astonishes through dramatic eruptions or shifting continents. Instead, it provides confidence. Measurements taken elsewhere gain meaning because they can be anchored to a surface that has remained largely unchanged across nearly the entire lifetime of the solar system. But even the language surrounding Callisto has changed. A moon once dismissed as little more than frozen rock is now often described as the Rosetta Stone of icy moon geology. The comparison reflects more than admiration. Just as an ancient inscription unlocked forgotten languages, Callisto helps researchers interpret histories written across worlds that continue to evolve. That transformation carries an unexpected lesson. Sometimes the greatest discoveries emerge from restless places. Sometimes they emerge from those that simply endure. Callisto reminds us that stillness is not the absence of meaning. In rare cases, it becomes the condition that preserves meaning with extraordinary fidelity, allowing the distant past to remain legible for anyone willing to look closely. A journey lasting many years is now carrying new questions toward Jupiter. Long before the destination comes into view, the instruments aboard the spacecraft are already shaping the future of how we understand Callisto and its hidden interior. The European Space Agency launched Jupiter Icy Moons Explorer on April 14, 2023. After crossing hundreds of millions of kilometers, which is about hundreds of millions of miles, the spacecraft is scheduled to arrive in the Jupiter system during the year 2031. Unlike earlier missions that briefly sampled Callisto while pursuing broader objectives, this expedition was designed with far more capable instruments and a much deeper scientific agenda. During its mission, Jupiter Icy Moons Explorer will perform 2 dedicated flybys of Callisto. Each encounter will gather measurements intended to examine the moon beneath its ancient exterior. Gravity observations, magnetic field measurements, imaging, and surface composition studies will work together rather than independently. Each dataset strengthens or challenges the others, gradually narrowing the range of possible internal structures. But one measurement has drawn particular anticipation: Scientists hope to refine Callisto's moment of inertia factor, the value describing how mass is distributed from the surface to the center. That single number carries remarkable importance. A lower value would indicate material concentrated toward the core, while a higher value supports the picture of an interior that never completed its separation into distinct layers. Uncertainty has remained since the Galileo spacecraft visited during the 1990s, and Jupiter Icy Moon's Explorer offers the best opportunity yet to resolve that question. Fresh magnetic field observations may prove equally revealing. If an electrically conducting ocean truly lies beneath the ice, Jupiter's changing magnetic field should continue inducing a measurable secondary response inside the moon. Improved observations may estimate the ocean's depth, thickness, and even its salt content with greater confidence than before. Another valuable instrument is the radar sounder, a system that sends radio waves beneath the surface to search for buried structures. Although designed primarily for Ganymede, it may also gather supplementary information during the Callisto flybys. If conditions allow, reflections from several kilometers below the surface, that is nearly 2 miles, could reveal boundaries hidden beneath ancient ice. Additional instruments broaden the investigation still further. A laser altimeter will map subtle changes in elevation. Spectrometers, instruments that identify materials by analyzing the light they reflect or emit, will improve our understanding of surface chemistry. Particle detectors will examine the energetic environment surrounding the moon, helping scientists connect Callisto's surface with the space around it. But beyond this ambitious expedition, no dedicated Callisto mission has yet received approval or funding. That reality gives these observations unusual weight. The discoveries returned after arrival in 2031 may shape scientific understanding of this distant world for many years. We have watched Callisto from afar, passed beside it, and assembled remarkable evidence from brief encounters. Soon we will look again with sharper eyes, seeking answers from a moon whose greatest surprises have come from what it concealed beneath an appearance of perfect stillness. As those answers emerge, our attention naturally shifts beyond what Callisto is, toward what a world like this ultimately means. Imagine placing your hand upon a landscape that has waited almost unchanged since the earliest chapters of the solar system. Beneath you would lie a surface whose story began before Earth had become the living world we recognize today, preserved with remarkable fidelity across an almost unimaginable span of time. The solar system formed approximately 4.57 billion years ago. Callisto's surface reached its enduring form within the first few 100 million years of that history, and meaningful geological renewal never followed. Since then, crater after crater has remained where it formed, building a continuous archive instead of replacing older chapters with newer ones. Now compare that timescale with our own. Modern humans have existed for roughly 300,000 years. Written history reaches back only about 5,000 years. The Industrial Revolution began around 250 years ago. Human spaceflight occupies less than 70 years. Against Callisto's chronology, every civilization, every language, and every telescope becomes an extraordinarily recent arrival. But the contrast grows even greater when we place Earth beside it. While our own planet transformed through shifting continents, rising mountain ranges, changing oceans, and evolving life, Callisto preserved the marks left by ancient collisions. Its oldest craters were already billions of years old before the first fish appeared in Earth's seas. Entire branches of evolution unfolded, while those same impact scars remained almost exactly as they had been. Few places elsewhere in the solar system offer such continuity. Mars experienced geological activity Within the past few 100 million years, the moon retained volcanic activity into the last billion years of its history. Even worlds that appear ancient often reveal episodes of renewal. Callisto stands apart because almost nothing has rewritten its oldest terrain across more than 4 billion years. That extraordinary persistence creates an opportunity unlike any other. Every preserved crater contributes to a record of the changing bombardment environment throughout nearly the solar system's entire existence. Scientists can compare crater sizes, densities, and distributions across the surface, reconstructing how populations of wandering objects evolved through immense stretches of time. Instead of scattered fragments, Callisto presents a remarkably complete chronicle. But the significance reaches beyond measurements alone. If you stood upon that frozen ground, every step would rest on material that has remained exposed since long before forests spread across Earth, before dinosaurs appeared, and before mammals became dominant. The permanence would not exist merely as an inspiring thought. It could be measured, mapped, and verified within the rocks beneath your feet. We often think of change as the force that gives places their meaning. Callisto suggests another possibility. By changing so little, it became one of the most valuable witnesses in the solar system. Every preserved impact, every weathered ridge, and every ancient basin endured while neighboring worlds continued evolving. In that enduring landscape, memory became physical. As everything else transformed, Callisto remained, carrying forward a record that almost nothing else was able to keep. Some worlds reveal themselves through constant transformation. Others speak by preserving what almost every neighboring world allowed to disappear. As we arrive here, we begin to understand that Callisto belongs entirely to the second kind. Across the solar system, the earliest chapters have been revised again and again. Internal heat lifted mountains, melted crusts, opened volcanoes, and buried ancient landscapes beneath younger ones. Erosion reshaped surfaces. New impacts erased older scars. Time became an editor, removing details with each passing age until only scattered fragments remained. Earth preserves remarkably little from before 4 billion years ago. The oldest surviving rocks are isolated, incomplete, and often debated. Mars retains hints of its earliest history, yet much of its first billion years has vanished beneath later geological change. Venus transformed even more dramatically. Its visible surface is estimated to be no older than about 500 million years, leaving almost nothing directly exposed from its distant beginnings. But Callisto followed another path. Its record remained open. Craters formed during the late heavy bombardment still occupy the places where they first appeared. Even older impacts also remain, layered beneath and around younger scars in patterns that scientists continue decoding today. Vast multi-ring basins preserve evidence of collisions that occurred before dinosaurs walked Earth, before vertebrates emerged from ancient seas, before the Cambrian explosion filled the oceans with complex life, and before oxygen became a significant part of Earth's atmosphere. Each preserved impact adds another page to a history that would otherwise have disappeared. By measuring crater sizes, overlaps, and distributions, researchers reconstruct the changing population of objects that once crossed the young solar system. The surface does more than display individual events. It preserves their sequence. Cause follows cause across billions of years without interruption. We usually think of memory as belonging to living minds. It seems inseparable from awareness, intention, and experience. Callisto possesses none of those qualities. It does not observe. It does not remember in the human sense, yet its frozen exterior has retained evidence that nearly every other large world has erased. The memory exists within stone and ice rather than thought. But that distinction makes its role even more remarkable. The moon became the solar system's archivist through the absence of change rather than the presence of activity, because it never generated enough internal energy to continually renew itself. It also never destroyed the oldest records written across its face. Its greatest scientific strength emerged directly from what it failed to become. That relationship is almost perfectly balanced. The less geological work Callisto performed, the more history remained available for us to examine. The more history remained, the more accurately we can reconstruct the earliest environment in which planets and moons were assembled. Preservation became knowledge across immense stretches of time. As our perspective widens beyond Jupiter, Callisto begins to represent more than a single distant moon. It becomes a reminder that countless worlds orbiting other stars may also carry histories almost untouched beneath ancient surfaces. Somewhere among them may exist other enduring archives, waiting through billions of years until someone finally learns how to read what they remembered. The farther we widen our view, the less exceptional Callisto begins to seem. Its story is not the result of unusual physics or improbable coincidence. It emerges from rules that operate wherever gravity gathers ice, rock, and time around a giant planet. Those rules shaped Jupiter's family of moons into something resembling a miniature planetary system. Four large worlds formed from broadly similar ingredients, yet each followed a different path. Their futures depended upon orbital distance, gravitational interactions, and whether neighboring moons locked them into lasting resonances that continually supplied internal heat. A difference established early endured across billions of years. But Jupiter is only one example. Saturn presents another variation on the same theme. Enceladus circles much closer to its parent planet and remains trapped in a gravitational resonance with Dione. That repeating interaction flexes its interior, sustaining an active ocean and towering geysers. Far beyond, Iapetus occupies a colder and more distant orbit. It is geologically ancient, inactive, and coated with a striking contrast between bright and dark terrain. Although every moon has its own history, Iapetus shares an important resemblance with Callisto. Both preserve landscapes that have experienced remarkably little internal renewal. The pattern should extend beyond our own planetary neighborhood. Around giant planets orbiting distant stars, the same physical laws govern the evolution of large icy moons. Some may occupy resonant orbits that maintain warm oceans beneath frozen crusts. Others may circle just beyond those gravitational relationships, receiving too little internal heating to awaken their interiors. They would remain cold, stable, and enduring, preserving ancient surfaces while neighboring moons continued changing. If giant planets prove common throughout the galaxy, then worlds resembling Callisto may also exist in extraordinary numbers. There could be billions of large, ice-rich moons resting beyond the strongest gravitational influences of their parent planets. Across immense spans of time, each would accumulate impacts without erasing them, gradually becoming an archive of its own planetary system's earliest bombardment history. But those distant archives would remain unread until someone learned how to interpret them. Every preserved crater would contain information, yet information alone is not knowledge. Knowledge appears only when curious minds recognize patterns, compare records, and discover the physical processes connecting them across time. Suppose life has emerged elsewhere among those countless stars. Suppose another civilization eventually built observatories, launched spacecraft, and explored the frozen outskirts of its own planetary system. It might also discover that the most enduring witness was neither the brightest world nor the most active one. Instead, the oldest testimony could come from the moon that changed the least. That possibility returns us to our own place in the story. We became the species that learned to read landscapes as history rather than scenery. By measuring ancient scars, tracing invisible oceans, and following the mathematics written into frozen surfaces, we uncovered memories preserved long before our own existence. Callisto reminds us that the universe keeps remarkable records and that understanding begins when someone finally learns how to read them. Long before we could measure distant moons, we simply watched the sky. The brightest lights returned with dependable rhythm, yet their true nature remained hidden beyond the reach of human sight. Jupiter crossed the heavens countless times, while its largest companions traveled beside it, unseen by every civilization that recorded the stars. Everything shifted in January of 1610. Using a telescope refined from earlier Dutch designs, Galileo Galilei noticed four tiny points of light beside Jupiter. Night after night, their positions changed. They did not wander randomly. They circled the giant planet. That simple observation carried extraordinary weight. You and I can recognize it as one of the moments when the universe became larger than familiar assumptions allowed. But recognizing those distant moons was only the beginning. For centuries, they remained little more than moving lights, their surfaces concealed by distance. Human imagination filled the gap where observation could not. Only after spaceflight became possible did those distant companions begin revealing individual identities instead of remaining anonymous dots against darkness. In the late 1970s, the Voyager 1 spacecraft and Voyager 2 spacecraft crossed the Jupiter system, sending home the first close views of the Galilean moons. Suddenly, each world possessed a distinct character. Io blazed with active volcanoes unlike anything previously seen. Europa displayed fractured plains of bright ice. Ganymede revealed sweeping grooved landscapes. Callisto appeared ancient beyond expectation, its face covered almost completely by overlapping impact scars accumulated across immense spans of time. But the deepest transformation arrived during the 1990s. The Galileo spacecraft remained within Jupiter's domain for years instead of rushing past. Repeated encounters allowed scientists to measure gravity, magnetic fields, and subtle changes impossible during brief flybys. Evidence accumulated for liquid water beneath Europa's frozen shell. Ganymede emerged as the only known moon generating its own internal magnetic field. Callisto, once dismissed as little more than a battered relic, revealed signs that a buried ocean could still survive beneath its ancient exterior. The mission eventually reached its planned conclusion in September of 2003. Engineers commanded the spacecraft to descend into Jupiter's atmosphere, where enormous pressures and temperatures destroyed it completely. The decision carried unusual significance. Galileo still functioned, yet humanity deliberately ended its journey to eliminate even the smallest possibility that future orbital changes might carry terrestrial microorganisms toward Europa, where an ocean beneath the ice could perhaps support life. Pause with that thought for a moment. We chose caution over convenience across roughly 628 million kilometers, which is about 390 million miles. Of space, we protected a habitat no human had entered, preserving possibilities that remained entirely hypothetical. That choice reflected something new about our species. As we learned to read the histories preserved within ancient worlds, we also learned that exploration carries responsibility. Understanding lifeless landscapes sharpened our awareness of living ones, even those that may exist only as careful scientific possibility. In seeking the oldest records written across frozen moons, we began discovering a different record within ourselves, one measured by curiosity, restraint, and respect for life, wherever it may someday be found. We often admire motion before we understand endurance, a world that erupts, fractures, or reshapes itself seems alive with purpose, while another that changes almost imperceptibly appears to have fallen behind. You can feel that instinct even when looking across the solar system, where activity seems to promise significance and stillness appears to suggest defeat. By that measure, Callisto seems to have lost every comparison. Io reshaped itself through relentless volcanism. Europa concealed its past beneath younger ice. Ganymede developed a layered interior and its own magnetic field. Their stories continued to unfold across billions of years. Callisto remained almost exactly as it had become near the dawn of the solar system. But that is only one way to understand change. Another view asks, what survives instead of what transforms? Through that lens, permanence becomes a rare achievement rather than an absence of progress. The surface before us has carried an uninterrupted geological memory across nearly the full history of the solar system, preserving events that vanished elsewhere long ago. Entropy is the tendency for ordered systems to become increasingly disordered as time passes. We encounter it everywhere, from weathering mountains to fading memories. Information is gradually scattered, structures wear down, and histories become harder to reconstruct. Yet Callisto resisted that pattern more successfully than almost any other large world we know. It retained evidence instead of replacing it. Consider its neighbors again. The volcanoes of Io buried almost every trace of the moon's earliest landscape beneath younger lava. Europa repeatedly renewed its icy shell until ancient terrain disappeared from view. Earth recycled its crust through plate tectonics, erosion, and volcanic renewal, leaving only scattered fragments approaching 4 billion years in age. Mars preserved more, yet even there, volcanic plains, flowing water, wind, and ice altered enormous regions across immense spans of time. But Callisto continued accumulating history without wiping the slate clean. Each impact joined those already present. Every basin remained part of the same expanding archive. The oldest scars stayed visible while younger ones settled among them, producing a layered chronology that scientists can still read today. Few worlds have offered such uninterrupted testimony. That continuity changes the meaning of the word dead. In planetary science, the term usually describes a body lacking substantial internal geological activity. It says little about scientific value. A world without volcanoes or shifting crust can preserve knowledge that energetic worlds inevitably erase. The absence of dramatic transformation becomes the very reason its record survives. Perhaps our language has encouraged the wrong impression. We hear the word dead and imagine emptiness. Yet Callisto resembles a vast library whose shelves have remained undisturbed across almost the entire age of the solar system. The volumes are written in ice and stone instead of paper. Their pages are impact basins, crater walls, and ancient plains. Nothing speaks aloud, yet every preserved surface carries another chapter. If you stood there, surrounded by landscapes older than complex life on Earth, you would not witness constant motion. You would witness duration itself. That perspective invites us to measure importance differently, recognizing that some places illuminate the universe precisely because they endured while nearly everything around them continued to change. Stand for a moment within the evidence rather than above it. Picture yourself on Callisto, treating the experience as a scientific exercise in perspective instead of imagination alone. Everything around you would be measurable, observable, and astonishingly old, inviting you to compare human time with planetary time through direct experience rather than abstraction. The ground beneath your boots would consist of water ice mixed with rocky material, darkened by the gradual accumulation of dust that settled across billions of years. In regions facing the sun, temperatures would linger near minus 140 degrees Celsius or minus 220 degrees Fahrenheit. Shadows would be colder still. Every grain beneath your feet would belong to a surface that has endured almost unchanged since the earliest chapters of the solar system. But the landscape would reveal very little movement. Horizons would rise and fall through overlapping impact basins instead of mountains built by shifting crust. Crater rims would stretch into the distance, intersecting older scars that had survived countless ages. Your footprints would become among the newest marks ever placed upon that terrain, joining a record separated from the previous natural alteration by spans of time beyond ordinary comprehension. Above you, the sky would remain perfectly black. There would be no atmosphere capable of scattering sunlight into familiar shades of blue. Stars would remain visible even while the sun illuminated the frozen ground. Every point of light would appear with unusual clarity, sharing the same sky as the immense planet that dominates Callisto's existence. Jupiter would occupy roughly 1.7 degrees of the sky, appearing about 3.5 times wider than the full moon seen from Earth. Broad orange and white cloud bands would wrap around its enormous globe. The Great Red Spot could be seen as a vast, swirling oval. Over the course of hours, neighboring moons would drift across its face, reminding you that even the giant above remains part of a larger celestial rhythm. But the greatest mystery would lie beneath your feet rather than overhead. Scientists estimate that a subsurface ocean, if present, may rest roughly 150 kilometers below the surface, that is nearly 93 miles. Above it would stand an ice shell thicker than any glacier on Earth. Below it would exist complete darkness. The water may have remained liquid for hundreds of millions of years, insulated by pressure and the lingering warmth of the interior. No one yet knows whether that hidden ocean is entirely sterile. No one can honestly claim otherwise. We possess evidence, measurements, and increasingly refined models, yet certainty still waits beyond the reach of present exploration. Standing there, you would occupy the meeting place of two profoundly different stories. Beneath your boots would rest one of the oldest preserved surfaces in the solar system. Beneath that ancient crust might survive an unseen ocean that still guards unanswered possibilities. Together they remind us that Callisto is more than a frozen moon. It is a place where memory and mystery coexist, inviting us to consider what truly deserves our attention across the vast history of the universe. Before oceans gathered on Earth, or continents found lasting shapes, another story had already begun, far beyond the inner planets. Callisto emerged within a broad disk of gas, dust, ice, and rock circling the young Jupiter, while the giant planet itself continued settling toward the form we recognize today. You and we can trace that beginning through physics, yet its scale still stretches beyond ordinary imagination. The solar system surrounding that newborn moon scarcely resembled the orderly place we know now. Planetary orbits continued shifting through gravitational encounters. Countless smaller bodies crossed unstable paths. The familiar arrangement of the rocky inner planets had not fully emerged. The asteroid belt had not settled into its present structure. Earth possessed no oceans, no atmosphere capable of supporting life as we know it, and no living organism had yet begun its long evolutionary journey. Callisto gathered from that restless environment. Material accumulated slowly enough that much of its earliest heat escaped before the interior could fully reorganize. Layers that formed inside neighboring worlds never developed to the same degree. The moon froze with much of its original structure preserved, carrying forward an ancient condition while the surrounding solar system continued changing in remarkable ways. But those neighboring worlds followed dramatically different paths. Io became the most volcanically active body in the solar system, constantly rebuilding its surface through immense eruptions. Europa developed into an ocean world whose hidden waters are considered valuable enough that spacecraft are deliberately protected against carrying terrestrial contamination. Ganymede formed a deep metallic core capable of sustaining the magnetic field that still surrounds it today. Meanwhile, far closer to the Sun, Earth became the place where chemistry eventually crossed into biology, biology into intelligence, and intelligence into the ability to study distant moons. Callisto remained something else entirely. It became the enduring record of the beginning. Its cratered plains preserved the earliest surviving chapter of our planetary neighborhood with extraordinary fidelity. While neighboring worlds repeatedly revised their histories, this ancient moon retained page after page of its original account, allowing later observers to compare what endured with what transformed. The universe often develops increasing complexity across time. Clouds collapse into stars. Stars produce the elements required for planets. Planetary environments sometimes support chemistry of growing sophistication. In rare circumstances, chemistry becomes life, and life develops minds capable of wondering how everything began. But that broad tendency does not require every world to follow the same path. Some remain comparatively simple, and their simplicity carries knowledge unavailable anywhere else. Because of that, Callisto is far more than an overlooked companion of Jupiter. It serves as a baseline against which change itself can be measured. It is the control in an experiment conducted across billions of years, preserving conditions that disappeared almost everywhere else. As our journey approaches its final reflection, we carry that perspective with us. The oldest frozen moon has shown that remaining unchanged can reveal as much about the universe as every world that transformed around it. Tonight, while you and we share this moment beneath Earth's sky, Callisto continues its patient journey around Jupiter. It circles the giant planet at a distance of 1,883,000 kilometers, which is about 1,170,000 miles, completing each orbit in about 16 days and 17 hours. It has followed essentially this same path since its early migration through the disk surrounding young Jupiter came to an end roughly 4,570,000,000 years ago. Across that immense span of time, remarkably little has altered its outward appearance. The landscape visible today would have seemed familiar when the earliest fish spread through Earth's oceans. It would have looked much the same as forests first expanded across the continents. It already carried its countless craters when our earliest human ancestors raised their eyes toward the night sky, searching for patterns among distant lights they could never have imagined reaching. Nothing significant has erased those ancient marks. Every major collision remained where it happened. Every basin survived. Every crater contributed another page to a record stretching back toward the beginning of the solar system itself. You are looking at history preserved in the original material rather than reconstructed from scattered fragments. Few places offer that privilege, but almost every other large world chose a different path through nothing more than the conditions established at birth. Internal heat reshaped landscapes. Volcanoes buried older terrain. Tectonic forces folded crust into new forms. Ice shifted, oceans moved beneath frozen shells, and entire surfaces renewed themselves across immense spans of time. Their stories continued through change. Callisto told its story through endurance. That endurance did not arise from determination or extraordinary strength. The balance of gravity, distance, and accumulated heat simply left too little energy for extensive geological renewal. Before deep internal transformation could fully unfold, much of that energy escaped into space. The moon settled into lasting stability, preserving what nearly every comparable world eventually replaced. What first appeared to be a limitation became an irreplaceable scientific gift. There is something deeply human in recognizing the value of that preservation. We often celebrate transformation, invention, and constant renewal because they shape our own experience of life. Yet the oldest truths sometimes survive because something remained almost exactly as it was. Callisto became the keeper of a beginning that vanished elsewhere, allowing later generations to reconstruct events no witness could ever have observed directly. We now examine this distant moon with instruments that would have exceeded even the boldest expectations of Galileo. The closer we study it, the richer its story becomes. The world once dismissed as empty reveals itself to be filled with evidence, memory, and context extending across almost the entire history of our planetary neighborhood. And tonight, above Jupiter's swirling cloud tops, Callisto continues its steady orbit. It carries the oldest surviving record among the great worlds, unchanged enough to remember what nearly everything else forgot. As we learn to ask better questions, it remains there, holding the beginning with extraordinary faithfulness, ready to answer through the language of stone, ice, and time.